The queen. Every ant colony starts with one individual, not a general, not a council, not a group decision. One ant, alone, who builds everything from nothing. That ant is the queen, and her role is both simpler and more extreme than most people realize. The queen has one job: reproduce. That's it. She doesn't lead the colony in any strategic sense. She doesn't give orders, and she doesn't manage day-to-day operations. The colony runs itself through chemical signals and behavioral instinct. What the queen provides is the colony's entire future, one egg at a time. Most queen ants begin their lives with wings. After hatching, they participate in a mating flight, leaving the nest, flying high into the air, and mating with multiple males in a single event. She stores all the sperm she'll ever use from these males in a specialized organ called the spermatheca, which she'll draw on for the rest of her life to fertilize eggs on demand. After the mating flight, she lands, tears off her own wings, she'll never need them again, and begins building the first chamber of what will become the colony. In the early days, she's completely alone. She seals herself into a small underground chamber, lays her first eggs, and raises the first generation of workers entirely by herself, feeding them using nutrients from her own dissolving flight muscles, the same muscles that carried her wings. Once those first workers emerge, she never has to care for eggs again. From that point on, she does nothing but lay, and she lays constantly. A mature queen of some species can produce over 1,000 eggs per day, every day, for decades. Some leafcutter ant queens have been documented living for over 20 years, producing hundreds of millions of offspring over their lifetime. The entire colony, every worker, every soldier, every new queen, originates from her. She also controls the colony's composition through the eggs she lays and the chemical signals she releases. Fertilized eggs become female workers or future queens. Unfertilized eggs become males. The ratio of castes, the size of workers, the timing of new queens, all of this is influenced by the queen's output. She is less a leader and more the colony's engine. Everything else exists to keep that engine running. The workers. If the queen is the engine of the colony, the workers are everything else. They build, they feed, they clean, they protect, they explore, and they carry the dead. A single worker ant lives only a few weeks to a few months, but during that time she cycles through almost every task the colony needs to survive. This isn't random. Worker ants follow a predictable age-based progression through different roles, a system called temporal polyethism. Young workers stay inside the nest doing the safest jobs. As they age, they move to progressively more dangerous work until, at the end of their lives, they're the ones venturing furthest from the colony into the most exposed environments. The colony essentially sends its oldest members out first, but within this general progression, there are distinct, specialized roles, each one critical, each one irreplaceable. Nurses. The youngest workers in the colony are the nurses, and their job is the most fundamental, keeping the next generation alive. Nurses spend their time in the deepest, most protected chambers of the nest, where the eggs, larvae, and pupae are kept. They lick the eggs constantly to prevent fungal growth, turning them regularly to ensure even development. They feed the larvae with regurgitated food and glandular secretions, adjusting what they provide based on what type of ant the larva will become. A larva destined to become a large soldier gets fed differently than one that will become a small worker. The nurses make these distinctions through chemical signals, responding to the specific pheromones each larva produces. When conditions change, temperature shifts, a disturbance in the nest, a threat approaching, nurses are the first to respond by moving the brood to safer chambers. They carry eggs and larvae in their mandibles, relocating them deeper or to a different section of the nest, prioritizing the youngest and most vulnerable. In emergencies, the survival of the brood takes priority over everything else. Nurses will relocate eggs before they even think about running themselves. Builders. Slightly older than the nurses, builders are responsible for the physical structure of the colony. They excavate tunnels, construct chambers, repair damage, and expand the nest as the colony grows. This is not simple digging. Ant architecture is genuinely complex, and the results reflect it. builders move soil particles and debris grain by grain, shaping tunnels with specific widths to allow two ants to pass each other without slowing down, angling chambers to take advantage of natural temperature gradients, and positioning the nest's layout to control moisture and airflow. Some species incorporate gravel, plant fibers, or wood pulp into their construction to reinforce walls. Leafcutter ant nests can extend several meters underground with hundreds of distinct chambers, each serving a specific purpose. Builders also respond to damage rapidly. If a tunnel collapses or a section of the nest is breached, builders mobilize immediately, plugging gaps with their bodies while others work around them, reinforcing weak points and rerouting traffic through intact sections. The nest is never truly finished. It's a continuously maintained structure that grows and adapts as long as the colony exists. Farmers. Not every ant colony farms, but in the species that do, the farmers represent one of the most sophisticated behaviors in the entire insect world. Leafcutter ants are the most well-known example, and their farming operation is extraordinary. Leafcutter farmers don't eat the leaves they cut. They carry them back to the nest, chew them into a pulp, and use that pulp as a growth medium for a specific species of fungus that the colony cultivates underground. This fungus is the colony's primary food source. The ants tend it like a crop, pruning sections that grow too large, removing diseased portions, adding fresh leaf material, and maintaining the specific temperature and humidity conditions the fungus needs to thrive. The relationship between leafcutter ants and their fungus has existed for approximately 50 million years. The fungus has been cultivated by ants for so long that it can no longer survive outside the nest. It's completely dependent on the ants for its existence, just as the ants are dependent on it for food. Neither can survive without the other. Farmers also manage a secondary threat, parasitic fungi, that can destroy the crop. They apply antibiotic compounds produced by bacteria living on their bodies to suppress these pathogens, effectively using a naturally occurring pesticide to protect their food supply. This isn't instinct in the simple sense. It's an adaptive, responsive behavior that changes based on the specific threat present. Foragers. Foragers are the most visible ants, the ones you see marching in lines across pavements and kitchen counters. They're also among the most important members of the colony, responsible for finding, collecting, and transporting every piece of food the nest consumes. In many species, foragers account for a significant portion of all worker deaths, simply because their work takes them furthest from safety. A forager's day is built around two things: finding food and communicating what she found. When a forager locates a food source, she doesn't just eat and return. She assesses the source, its size, quality, and distance from the nest, and makes a calculation about whether it's worth recruiting others. If it is, she returns to the nest while laying a pheromone trail from the food source back to the entrance, a chemical road that other foragers can follow. The strength of the trail she lays reflects the quality of the food. A poor source gets a weak trail, which attracts fewer ants. An exceptional source gets a strong trail, which draws large numbers quickly. As more ants travel the trail and reinforce it, it becomes stronger still. When the food runs out, returning ants stop adding to the trail. It evaporates, and forager traffic naturally redirects elsewhere. The whole system is self-regulating without any individual ant overseeing it. Foragers also adapt their routes based on efficiency. Given multiple paths to the same food source, forager traffic naturally concentrates on the shorter route over time, as ants traveling the shorter path return and reinforce their trail faster than those on longer paths. The colony effectively solves shortest path problems without any ant being aware it's doing so. Beyond food collection, foragers are responsible for assessing the quality of food before bringing it back. They taste and smell potential sources, rejecting anything that smells of decomposition, mold, or chemical contamination. In some species, foragers who encounter potentially harmful substances return to the nest and actively avoid the recruitment trail, effectively warning others away from a dangerous source without any direct communication. In larger colonies, forager teams operate in relay systems. One group collects food near the source, passes it to a second group at an intermediate point, who passes it to a third group closer to the nest. Each group specializes in a specific stretch of the route, reducing the total distance any individual ant has to travel and dramatically increasing the speed at which food moves from source to nest. It's demanding, relentless work. Foragers leave before dawn in many species and return after dark. Their bodies wear out faster than almost any other caste. Their legs literally deteriorate from the constant movement across rough terrain. An ant that begins foraging typically lives only a few more weeks before her body gives out entirely. She spends those weeks feeding everyone else. Scouts. Before the foragers can collect anything, someone has to find it. That job belongs to the scouts, a smaller group of experienced older workers who venture out ahead of the forager teams into unknown territory. Scouts operate largely alone, covering wide areas quickly and assessing everything they encounter. When a scout finds a promising food source, a new nesting site, or a potential threat, she returns to the colony and communicates what she found through a combination of pheromone signals and physical behavior. In some species, scouts perform a form of tandem running, leading a single nestmate back to a location to confirm it before broader recruitment begins. Scouts are also responsible for evaluating potential new nest sites when a colony needs to relocate. In species like Temnothorax, scouts will visit multiple candidate sites, assess each one based on factors including entrance size, interior space, light levels, and proximity to threats, and then return to the colony and effectively vote for their preferred site by recruiting nestmates toward it. The site that attracts the most recruits fastest wins, and the colony moves. No single ant makes the decision. It emerges from the collective behavior of dozens of scouts, each advocating for what they individually assessed as the best option. Cleaners. A colony of millions of ants living in an enclosed underground space produces an enormous amount of waste, dead organic matter, and potential contamination. Without constant maintenance, the nest would become a breeding ground for pathogens that could devastate the population. Cleaners prevent this. Cleaners remove debris from the nest continuously, carrying food scraps, shed exoskeletons, and other waste to designated disposal chambers or midden heaps outside the nest entrance. They groom nestmates by licking their bodies to remove parasites, fungal spores, and contaminants, paying particular attention to the queen and the brood. Some ant species have specialized cleaners whose role focuses almost entirely on grooming the queen, keeping her free of pathogens that could compromise her reproductive output. When disease enters the colony, a bacterial infection, a parasitic fungus, a contaminated food source, cleaners are often the first responders, isolating sick individuals, removing contaminated material, and increasing grooming activity in affected areas. Research has shown that ant colonies exposed to fungal pathogens dramatically increase their social grooming behavior within hours, spreading small doses of the pathogen through the healthy population in a way that triggers immune responses colony-wide, essentially a form of distributed inoculation. Undertakers. Every colony produces death, and death inside a nest is a serious problem. A dead ant releases chemical compounds as it decomposes, including oleic acid, which triggers alarm responses in living ants, and can attract pathogens if left unaddressed. Undertakers handle this. When an ant dies, undertakers locate the body within minutes, carry it out of the nest, and deposit it in a designated graveyard area, often a specific location, away from both the nest entrance and the foraging trails. This happens quickly, consistently, and without hesitation. Researchers who painted live ants with oleic acid found that other ants immediately attempted to carry them to the graveyard, regardless of the fact that the dead ant was still moving and resisting. The chemical signal overrides everything else. Dead means dead, and dead gets removed. Undertakers have been found to have different immune profiles than other workers, with stronger resistance to the pathogens they regularly come into contact with. They also tend to remain physically separated from the rest of the colony after handling bodies, reducing the risk of spreading contamination. In some species, undertakers who have handled a large number of corpses will self-isolate near the nest entrance, rather than returning to the deeper chambers where the brood is kept. And if you want to see more videos breaking down the hidden worlds of insects and the bizarre systems that keep them alive, subscribing means you won't miss what's coming next. The soldiers. Not every ant colony has soldiers. In smaller, simpler species, workers handle defense alongside everything else. But in larger, more complex colonies, a dedicated soldier caste exists. Individuals that are physically distinct from workers, built specifically for combat and defense, and incapable of doing much else. Soldiers are typically larger than workers, with disproportionately large heads that house the powerful mandible muscles they rely on. They're not generalists. They don't forage, they don't nurse, they don't build. Their entire biology is optimized for one purpose: protecting the colony. And the ways different species have evolved to do this are remarkably varied. Attackers. When a threat is identified, a rival colony, a predator, a human foot that came down too close to the nest, attacking soldiers move toward it rather than away from it. Their role is direct, physical confrontation, and different species have developed very different tools to carry it out. The most straightforward weapon is the mandible. Army ant soldiers have mandibles so large and powerful that they cannot feed themselves. Their jaws are built purely for cutting through other insects, small animals, and anything else that gets in the colony's path. Army ant colonies on the march can strip a small animal to the bone in hours, not because each individual ant is dangerous, but because they act in coordinated masses, overwhelming anything that can't move faster than they can swarm. Some species use venom as their primary weapon. The bullet ant, found in Central and South American rainforests, delivers a sting widely considered the most painful of any insect in the world. A burning, sustained agony that has been described as feeling like being shot, lasting up to 24 hours. Jackjumper ants in Australia combine powerful mandibles with a venom potent enough to cause anaphylactic shock in sensitive individuals, and they're aggressive enough to pursue perceived threats actively rather than waiting to be provoked. Chemical weapons are used by several species. Wood ants are capable of spraying formic acid from their abdomens with surprising accuracy, hitting targets several centimeters away and causing significant irritation and damage to the exoskeletons of rival insects. The carpenter ant takes chemical offense to its extreme conclusion. Certain soldiers can voluntarily rupture their own bodies, spraying a toxic adhesive secretion in all directions that immobilizes or kills nearby enemies, sacrificing themselves to protect the colony. Fire ants combine both venom and coordination in a way that makes them particularly dangerous. A single fire ant sting is painful but manageable. But fire ants rarely sting alone. They anchor themselves with their mandibles and sting repeatedly. And when one releases an alarm pheromone, others nearby join the attack within seconds. A large fire ant mound, disturbed aggressively, can produce thousands of simultaneous stings on a single target in under a minute. Defenders. Not all soldiers are built to attack. Some species have evolved defensive specialists whose role is to stop threats before they enter the nest, rather than chase them down after the fact. The most striking example is the Pheidol genus and several similar species that produce what are called doorhead or plughead soldiers, individuals with flattened, disc-shaped heads that function as living doors. When a threat approaches the nest entrance, these soldiers back into the tunnel opening and use their heads to physically seal it, their head shape matching the entrance diameter almost perfectly. They stay there until the threat passes, immovable, essentially becoming part of the architecture. Colobopsis truncata, a European species, takes this further. Their major soldiers have heads shaped specifically to fit their nest entrances, and they hold position for hours if necessary, only opening when a nestmate taps them with the correct internal signal. An ant without the right chemical signature gets no entry. This is a living lock and key system built into the ant's own body. Other defensive behaviors focus on early warning rather than physical blocking. Sentry soldiers in many species are stationed at the nest entrance continuously, antennae in constant motion, monitoring chemical signals in the surrounding air. At the first detection of an alarm pheromone released by any ant in distress anywhere near the nest, sentries immediately go into alert mode, communicating the signal inward to mobilize other soldiers deeper in the nest, while positioning themselves to intercept whatever is approaching. In some species, defensive soldiers form physical barriers with their own bodies during raids, linking together in chains across vulnerable tunnel openings, forcing attackers to physically break through multiple connected ants rather than a single individual. Each ant in the chain holds the next, and the chain holds the line. Attackers trying to breach the barrier face not one defender, but a coordinated wall of them, each one anchored and pulling against the intrusion. What makes ant defense so effective across all these different strategies is the same thing that makes every other aspect of the colony so effective. It's not individual strength. No single ant is particularly formidable. It's coordination, communication, and specialization operating simultaneously at a scale that turns a group of small insects into something that can hold off predators many hundreds of times their individual size. The colony survives not because any one ant is extraordinary. It survives because every ant, from the queen laying in the dark to the soldier holding the entrance, is doing exactly what it was built to do, and doing it at the same time as everyone else.